Hey, hello everyone. Good morning, good evening. This is Research Jam. We are at 14 now. That's a lot of jams. So today's going to be a very chill event. We have two presenters, so we can spend a lot of time on each of them. Without further ado, let's get started with Corbinian.
Okay, thanks. I have a presentation. Let me just share my screen. So, hi, my name's Corbinian. What I'm going to present today is essentially my master's thesis topic. I'm comp sci master student in Hamburg, and for the next 6 months, I'm essentially gonna deal with partial model merging. And at this point in time, it's just like I have an idea presentation, so I haven't written a single line of code. But yeah, there's a lot for me to do, and I just want to present the overall idea and maybe get some feedback at this point. So partial model merging already kind of gives away what this is going to be about. Nonetheless, I want to start with a really short primer on assembling and model merging. So let's say you have some strange spot on your skin that you're worried about. And what you do is you go to a doctor and tell them to look at it, and then they say, okay, it's very likely benign, and they have some kind of concepts, like some rules or methods that they use to determine that. So for example, they could say, okay, it has a small size, a consistent color, and it's symmetric. And all of these speak for that spot being benign and not, for example, skin cancer. And you don't really trust them. You want to hear a second opinion. So you go to a second doctor, and they are maybe less sure about the result, but they also say this is likely benign. And they may have a different mental model that somehow overlaps, but is slightly different. So for example, they might not care about the color as much, but are rather interested in it having a smooth border as a relevant criterion. So what typical assembling would do is just take the prediction of both models and average them. And in the real world, this is probably what you would do, right? You would simply take the answers of both doctors and take the average and say, okay, this is somewhat benign. And then maybe a short primer on model merging. So I guess there have been two presentations in the past already. I think the Git rebasin presentation and the repair presentation. So I guess many of you will be familiar with this. But just as a short recap, deep neural networks are invariant to the permutation of neurons as long as the incoming and outgoing weights are permuted to. So those two models that you see on the screen are functionally equivalent. For every input, they will output exactly the same activations. So when you do model merging, you essentially take two models and try to align them, and then take the average of the weights and biases. And this alignment process is a linear sum assignment problem, right? You try to maximize the cross correlation between either the activations or the weights. Now, these are some slides or figures that I took from the Git rebasin paper. There's a few issues with this method. So for example, it performs worse than assembling, right? The averaging of prediction vectors we saw before. And that is the case for models of identical size. So if I have two ResNet 50s and I merge them versus having two ResNet 50s and assembling them, then assembling them will typically be better in terms of loss and accuracy. And the other problem that you have when you want to do model merging is that in order to achieve what they call linear mode connectivity, so the same loss at every interpolation step between both models, you have to have models that are really, really wide. So for example, in the ResNet architecture, they needed a width multiplier of 32 to actually achieve constant loss along the interpolation of both models. And that is problematic because, for example, if you double the width of a neural network, you are quadrupling the number of weights that it has, because if it's fully connected, the relationship is approximately quadratic. So if you double the width, it's already worse than assembling two models of the same size. So thinking back to the doctor example, I mean, you could just take both models and merge them. but this is somewhat problematic. And maybe some insight as to why this might happen. So you have Dr. A and Dr. B, and they have their internal representations of the world. So those could, for example, be kernels that a CNN learned. And what you do for model merging is first you align them. So for example, small size might correlate with each other and symmetric as well. And then you merge them. But as you can see, some features you can merge and some you can't. So if you think these are neural network kernels in a CNN, then small size might represent like a small activation that is central and you can merge that, but the other ones would be incompatible. And this is a problem that actually occurs in real ResNets too. So for example, this is a figure from the appendix of the repair paper. And these are the activations of two ResNet 50s. And you see that some kernels, after you do the alignment, do match well, and some other kernels don't match well. And the reason is that both networks learn similar features, but they are, of course, not perfectly identical. So you can't always find a good matching. Yet those kernels that don't match get averaged, and what you get as an output is, I think, probably worse than just keeping either of them individually. And this is also the reason why wider models are easier to merge, or at least part of the reason, because if you have more candidates to choose from, there's simply a higher likelihood that you will find a matching kernel or a matching set of weights that makes sense to be merged with. So we have seen assembling and we have seen merging, and my idea is there has to be something in between. And this is essentially what I'm proposing in my thesis, which is partial merging. So in this case, the amount of overlap between both models would be a hyperparameter. In this case, it's like 2/3, because out of like a 3 neuron wide layer, you see on the right, if you have an overlap of 0%, you have something that's functionally equivalent to assembling. So how are those alignments being done in the background? So you have some neurons. Let's say you have a layer with 5 neurons in model A and model B, and you have cross correlations between them. And what you do is you simply treat this as a linear sum assignment problem, and you try to maximize the cross correlations, because as a greedy matching, this would give you the best solution to combine them. My proposed adaptation of this would simply be to relax that problem. So you can see we add like buffers as columns and rows, and those just have a perfect cross correlation of 1. So what happens if you compare to the previous slide is that those matchings that had the worst cross correlations before, so 0.69 and 0.87, those will now be assigned to the buffer zones. And exactly those are the neurons that will not be merged. So the parts that are kept individually. And of course, since it's fully connected, you would simply assign the remaining weights as being zeros. So, I mean, going back to the example of the doctors, for example, also this could mean small size and symmetric had a high correlation coefficient, and they will be matched. But consistent color and smooth border had a bad correlation coefficient, so they will be assigned in the buffer zone and then be kept separate. So the size of the model would increase, but this is still cheaper than assembling both models. And my assumption would be that it also has a better performance than doing a full merging. I have some loosely connected hypotheses that I believe are true. And the goal is to find out if that is actually the case. So for example, I think that features are either compatible or they are not compatible. So I believe that, for example, when you think, oh, how do you select the number of k for k-means clustering, you're typically looking for some kind of elbow bend, and then you select that as the number k. And I think the cross correlations might display a similar characteristic in their shape, but that there's like some kind of obvious point at which you should make a cut and then either merge or not merge neurons. I think that if you have two models that are trained on very similar data sets, so for example, exactly the same distribution over classes, then those should be easier to merge. I think that earlier layers, because they encode more primitive concepts, like for example, oriented edges, should be easier to merge than later layers because they encode more distinct, more specific features. And I also think that if you merge more than two models, then the average correlation coefficients of the last added one will also be lower because simply you have already more candidates to choose from when you assign neurons to neurons. And I also have some open questions that are only like loosely related. So for example, are those features that are commonly learned by both models, are those more robust, for example, to distribution shifts? What happens if we only keep exactly those neurons? So the overlapping part of both merged models, is the performance still good or does it go down very fast? Are models that are trained to have flatter optima, so for example, sharpness-aware minimization or stochastic weight averaging, are those easier to merge? Or in other words, can you achieve a higher overlap between them? Are those neurons that are easier to merge in any way related to those neurons that are being kept by pruning methods? Because then you could also merge pruned networks easier. Can you merge models easier if they have been fine-tuned on the same base model? So it's very common that if you have a ResNet, you simply take the ImageNet weights as your base and then you fine-tune on your specific data set. Can you merge models when they are in a compressed state? So for example, if you think low rank approximation, and also can you somehow automatically determine the overlap that you should choose compared to like having it as a hyperparameter that you actually think about versus the method chooses the hyperparameter itself? So please talk to me if you can either provide compute support because I will have to train tons and tons and tons of models. If you have application ideas, for example, this is something that could be very useful for federated learning, but maybe you have some ideas that go beyond that. And also if you maybe could think of any interesting ablation experiments. Yeah, and I guess that was the presentation.
Hey, Corbinian, awesome presentation. I love this. I love this idea. This halfway between ensembling and merging. Someone should do it if no one has yet. A couple thoughts. So actually, can you pull the slides back up?
Oh yeah, sure.
So on one of your slides, you mentioned the possibility of like a knee in this curve.
Yeah.
Maybe, yeah, an elbow bend. So I wanted to bring up a paper that I worked on with Yishwan Li. I'll paste it in the chat, called Convergent Learning. And basically, one of the things we did in this paper is produce these exact curves that you're talking about, correlation coefficient curves. So if you look at figure 3 and S3, you can see some example curves for one particular model. We were surprised to find that there was not as much of a knee, not as much of a sharp transition as you'd expect. Something like PCA or SVD, if you look at the coefficients, right, you'll see this like lots of big coefficients and then a drop off to, you know, 6 orders of magnitude less correlation or whatever. We found that wasn't really the case, and there's just like medium high correlation, medium correlation, a bit lower correlation, and there's not a huge drop off. So it might be worth just like making those plots early on to verify your assumption. Another hypothesis kind of floating around here, which I don't think you stated directly, is just that if you have multiple models and you find neurons that are more similar, it's more worth merging those and keeping the neurons that are dissimilar separate. In one hypothesis, that damages the network less, so that sounds like a great idea. There could be another hypothesis, though, which is that the features that are more similar between two models are the most useful features in those models, and any damage to those features would hurt the resulting merged model more. So I would love to see an ablation where you maybe you don't use the linear sum assignment method, but you preserve highly correlated features, and verify that in fact that merging is worse as you assume. Oh man. he just left. I mean, I'm used to people not liking my questions at all, but this is next level. Huh. Well, hopefully he'll be back. On my end, he had a bad connection for part of the talk. Did that?
Yeah.
You guys do? Okay. I was thinking though that his I really love his like buffer region approach where you just add a bunch of ones that allows you to use the same algorithm, linear sum assignment, and it'll automatically select the worst matches to be used in the buffer. I think he's back. Well,
sorry, I think my Wi-Fi just let me down.
All good. I thought my questions must have been super offensive.
Yeah.
Yeah, I guess, did you have any comment on the on that one assumption and whether merging mergeable features is better? Oh, there are two of you now.
So I got the comments on the paper that you mentioned and figure 3, and then I didn't hear anything anymore.
Okay. So I was saying, first, I really love your approach of using the buffer region of ones to automatically allow the same algorithm, linear sum assignment, to match the most unmatchable features to the buffer region. The most matchable features are automatically selected for merging. Beautiful, elegant, right? But one thing I'd love to see is an ablation study where you, rather than, let's say, forcing the most matchable features to be matched, you take the most matchable features and allow them to be preserved, one in one network, one in another network. In other words, you put those in the buffer region instead, because it might be that as you're kind of assuming, merged networks work best when you merge the most similar features and you preserve as distinct the kind of rare features that didn't have a match in the other network. Another hypothesis, though, is that the rare features were learned because they weren't that important, and the network just kind of like put its extra capacity over there. They didn't do much the whole time, which is why they didn't converge to anything shared between the networks. In that world, you would actually prefer just to discard those features and to maybe spend the extra capacity in the final network on near copies of very useful features. So you could do an ablation here where you just like manually put neurons in the buffer region, and it wouldn't be the same as your beautiful linear sum assignment, but I don't think that's needed. You could just select specific neurons. In fact, that's what linear sum assignment will already be doing, I think, is you just take the lowest neurons and manually put them in the buffer region, or the highest neurons, put them in the buffer region, and that'll allow you to do a more careful ablation. Probably also a random set, right, in the buffer region. I would love to see those ablations, and I have no idea what you would get, but I think it would be interesting.
Yeah, thanks.
Wouldn't just use the negative values of correlation, just do the trick so that the most correlated ones are being kept as individuals?
Yeah, I think that's exactly what would happen, right? Because typically LTAPs are like minimize instead of maximizing, so you already have to take 1 minus the correlation coefficient. I just like ignored that for the presentation. But I think if you just change the sign, it's exactly what would happen, right?
You would still want to have the best matches. When you are matching neurons, you would want the best ones selected for those matches, not the worst ones. So you just have to be careful about the signs and everything, but I'm sure it's doable.
Yeah, okay. And yeah, with either method, I think you probably want a figure that's starting from no merging at all, like the percentage growing, and then at the end, like fully merging, and see how that curve changes when you use different methods, and see if the curve is smooth, if there's like cutoff, which will help you decide on hyperparameter. But more importantly, probably it would just tell you more about why certain overlap ratio is best.
Yeah, I mean, ideally you would have something like a linear relationship, right? Where you have like as you match more and more parts, you get closer to the performance of regular model logic. And as you mentioned, less and less get closer to assembling. But it could be that somewhere in between it actually beats assembling.
Are you imagining you would be like fine-tuning the merged model for a while as well?
I didn't mention that. I mean, you could do that. I know that in some papers on model merging, they did that, but in most applied scenarios, the idea is to not do fine-tuning on the merged model because you, for example, don't have access to the data sets.
Sure.
One thing that I'm wondering, because in the Git rebasing paper, for example, they compare different interpolation ratios, right? They have 100% model A, 0% model B, and then 1090, 2080, and so on. And it's not as easy when you only partially merge. I mean, you can do exactly the same in the part that's overlapping, but in those parts that don't overlap, you always have the same relevance assigned to those neurons. So it could be a bit more difficult, or you just multiply them with 0.9 or 0.8 and just like scale down the activations, but I'm not sure if that's equivalent.
I think you could probably cast your process in those original terms by, so let's say you have model A, model B, and you now have an algorithm to create merged model AB, which is wider than either A or B. You could probably project A to a model that was as wide as AB with a bunch of zero weights filled in that was mathematically equivalent, maybe. Same with model B. And then you could actually do this linear interpolation between them and have it be such that your algorithm was actually the 0.5 point in the middle. If you want to be able to make those corresponding plots. I'm also curious though, it might be a dumb idea, but again, just for ablation's sake, what if you just kind of randomly selected individual neurons from each model and didn't do any weight mixing at all? So like for every neuron, you keep the incoming weights and outgoing weights. Would that work? But you don't linearly interpolate the weights. Like it's either from model A or model B, not mixed.
So if there's a good match, just choose one of them?
Yeah, I guess I'm still thinking of ablation where you don't even need to necessarily choose the best matches. You're just randomly choosing. Like if your model AB was a full twice the width of A or B, and you followed this random procedure, then I guess that means you would be choosing every single neuron from both models. So you would be running both models. You'd have a weight matrix that was half zeros, so kind of a little bit silly, but then the final predictions would only be added together at the logit layer, which I think might be equivalent to just full ensembling. Like both models are making their own decisions, their own computation paths, and then they're voting at the very end, which feels the same as ensembling.
But the function is the same.
You could do that, but without the full width of both models, right? I don't know if anyone's written a paper on that approach. But.
So one paper that I also know is model soups. So they essentially train 50 different ResNets on, I think it was ImageNet with different hyperparameters. And when they merge them, in the end, they get a performance that's better than each individual model, and I think also better than just assembling them. I'm not really sure why that happens, but I'd be curious as to how much of that dynamic I can still capture when I only partially merge them.
Yeah, model soup also allows, I think, more than 2 models to be merged. I don't remember how many, but
yeah,
you take a group and come up with one.
I haven't tried model soup, but I was just wondering, what is the trade-off there? Like, what is the incremental benefit you get from training 50 models versus the additional computational cost you incur for training 50 models? Like, what's the ROI?
I think the difference between just one all 50 was like maybe 2 or 3 percentage points. So it wasn't really big, but I mean, yeah.
well, the hypothesis there is usually after you finish a project, you have like 50 to 100 models laying around. It's like want to make best use of them anyways, because you're tuning all these hyperparameters, and their findings basically, oh, turns out if you just average all these seemingly mediocre models, you get an even better model. That was my read. Any questions or comments from the room for Corbinian?
I have a question, I guess. I feel this is probably not I'm unqualified, I feel like, to ask this question, but what is the question was asked by Ashish, what's the ROI? So I'm assuming that the metric he was calling out specifically was accuracy or precision, one of those two. What about other metrics? Like, what are any improvements, by other metrics, like I'm kind of giving my hand away here a little bit, like bias, stuff like that, like variance, you know what I mean? Like, are there any?
So I think my main metric would be test loss, and then secondary test accuracy, simply because that's also the metrics that were looked at in the Git rebasing paper. Which I think also are the two most important, right? Loss and accuracy. But then I think in the Git rebasing paper, they also found out that, for example, the like if your model predicts like class B with 80%, then it also becomes more aligned with that class actually being 80%, right? So you would have additional benefits from models being merged. And what I also am wondering, for example, is if you average the features together, does that maybe protect against membership inference attacks? Because the influence that one particular data point had on the training data set on the weights of the model might become smaller if you average them by merging. But those would be benefits that go beyond just like improving, for example, your loss or your accuracy. If that answers the question.
It does. Thank you.
Cool. A note for compute assistance. So we have a guide here where you can apply for compute support from MLC. So you can skip the proposal part because I already gave a presentation at ResearchGem, and just send an email basically to compute@mlcollective.org with your project name and your email. And that will do. Good luck there.
We'll do that. Thanks.
Also relevant there, I guess, for everyone. I think, Roseanne, correct me if I'm wrong, one of our grants expires in July, one of our compute grants. So
Yeah.
we have a bit of money left on that one. If people want to use it over the next, what is that, 2 months, 3 months, 2.5 months, now is a great time to run some experiments.
Yeah, we can fast track your application because of the time by expiration.
Better to use the money for sure.
Mm-hmm. All right, let's move on to Zach.
Awesome. I actually ended up throwing a few quick slides together. But yeah, it's probably a little bit rambly, so feel free to interject with any questions. Great. So broadly, I've been thinking, just for context, a lot about like how to evaluate large language models, specifically models with like that we interact with in text format, like a lot of these chatbots. I mean, I'm sure you've all seen all the like N+1, like we distilled a model from GPT-3 using like a much smaller model, but it's not really clear on how to evaluate them. I mean, I just threw a couple like background slides. So obviously there's a influx of a large influx of companies that are training models or building on top of LLMs. And kind of what I alluded to before, there's a lot of these models that are coming out now that are also distilling on top of OpenAI. So basically taking the outputs of GPT-3 or 4 and then training a model on a much smaller model to, you know, recover some of that like chat likeness. So you can maybe get around some of the RLHF that some of these larger models end up having to do. But the thing that has been tricky for me to understand is like, how do we really evaluate like how good some of these models are? So one of these recently released ones called Vicuña, they evaluated it using a GPT-4 as the like critic. So basically given I think a prompt, they ranked a bunch of models and where GPT-4 was the basically the critic and was able to rank, you know, these 4 models that they compared against. The main point that I like, or the main thing I've been thinking about recently has been that, so a lot of the models have, I guess there's these benchmarks like HelloSwag and ARC that a lot of people tend to evaluate these models on, but to me they don't seem to encompass, you know, some of the usefulness or the chat likeness that some people I guess use as a criteria for figuring out like which models are better, which models to use. Like, for example, to me, it seems it's not exactly clear on how people determine, you know, whether to use ChatGPT versus Claude or, you know, something from Cohere. Yeah, I've been thinking a lot about like how we can maybe leverage existing preference data that exists out there, or try to distill some synthetic data from some of these large language models like the ones from Anthropic and OpenAI to come up with a better evaluation or benchmark on like how useful and, you know, I guess preference aligned are these models. I know this is really hand wavy, but yeah, I'm kind of curious to hear people's thoughts on this. Like yeah, I guess I'll leave it at that for right now.
Can I was actually just thinking, you know, we are trying to remove manual stuff, but like a good and moving towards automation, but a good evaluation could perhaps be you generate a bunch of questions and farm it out to Mechanical Turk and say that you use you answer these questions using this model deployed in the cloud, and they rate it on a scale from, I don't know, 1 to 10. And I don't know, that just kind of struck me, like maybe using Mechanical Turk and humans to get a more empirical empirical assessment of how your interaction with a conversational model is.
Right. Yeah. That makes a ton of sense. And I think I've seen a few people do that. Obviously it comes with, you know, significant time and it is a little bit expensive. Yeah, one of the things that I was trying to wrap my head around was we have some of this existing preference data that I think Anthropic released, like the helpful and harmlessness data set, where given a prompt, here are the 2 responses, one that's chosen and rejected. And I was curious to think, you know, curious to hear if people would think it'd be worth trying to use that to maybe distill some preferences from existing like preference data, if that makes sense. So maybe one idea I had was maybe we could like train a reward model on that and then do some pairwise comparisons across many different models, and through that you can generate some sort of ranking or like an ELL score. Yeah, and if you know a lot of this didn't make sense, feel free to ask questions. I'm sure I glossed over a lot of things.
So on the bar chart that you showed, that's basically that, right? It's just using GPT-4 as a reward model, and to rank all the other models' responses.
Right. Yeah, so that was my understanding as well. But
yeah, but it's kind of heavyweight. So we're thinking if you have preference data, maybe you can train a really tiny just preference model, which only knows if this is gives you a preference score or something. It's not a full chatbot,
mhm.
and that would maybe do the job. I'm sure people are doing that. I don't know though.
Yeah. Yeah, I think one of the things that I was like, I think like the in general, like generating synthetic data with these models is pretty cool, but like for modeling preferences, I wonder how much yeah, I wonder like what biases like creep in with using something like ChatGPT, or like it's hard to know exactly like I mean, you could say this with everything, but it's hard to know like what the biases are on that model specifically.
Also, don't we have a reward model every time we RL HF? So for all these big models that are being trained, they have a bunch of valuation or preference reward models.
Are those released? Maybe I should.
No, but I wonder why not, because I'm guessing not big, small, and it doesn't really contain anything. And that might be the key to how one model is better than the other, is that their reward or like preference model is better trained.
Mhm.
That's why they don't release them. That's the edge.
Right. No,
I imagine for RLHF, choosing the human who would evaluate between a pair of responses, like what kind of human, I don't know how to better articulate it, but like that person's preferences would also kind of determine the bias and how biased the RLHF is, right? Or how good or bad the RLHF is.
Yeah, for sure. In the end, all these models, what they're competing the high quality human labelers or annotators. But after that process, I think there would be a reward model trained from the human preferences. So what we're wondering is, would those models, small models, be released? Can they be swapped? Can they be used to have a more generic evaluation suite that we can apply to all future large chatbots?
Right.
Those models are likely to be small, trained on small data, and then like probably quite limited, maybe very overfit to the data, so useful for steering a large model. But for example, if they were to be released, they could easily be hacked, or people could find examples where the model gives answers that seem opposite. Yeah. And if they were released, I'm sure people would do that on the internet. So I'm imagining companies don't want to release these tiny models because they know that they're like 80% right, 20% wrong, which is useful for steering a model, but it's not they're not going to provide like defensible great scores. That's my hunch though.
Yeah, but isn't that great if every one of us can just find vulnerabilities in those models? And well, they're releasing the bounty already. OpenAI is giving us their preference model would make it easier.
Yeah, no, that's interesting. Yeah, I don't know. Do you have any suggestions on things to, I guess, investigate, or like, I think I'm like interested in this because it's hard to know. Like, I'm just like, I'm very obsessed with like, evaluations, in the sense that like if you don't evaluate something, you don't really know the quality of it. So I think they'd be fun to work on, but I'm just not sure what the next right step would be.
It does seem like self-evaluation is growing in interests, which means using the model itself to evaluate itself. You can think of it as even within the same session, just looking at all the things that have happened, and you ask the model, what do you think? How safe do you think our past conversation has been? And it gives you a rating. And there has been studies out there saying it's pretty aligned with what humans would think. You can also start a separate session. So it's the same model, but 2 sessions evaluating each other. So those things are being done more and more. I'm a little concerned that we are, using models to evaluate models, the same model. It's going to be problematic and only accentuating the bias going forward. But I don't know. But that's the big trend.
In fact, I just to piggyback off Roseanne's comment on another session, so I'm very interested in medical applications of LLMs. And I heard there was a podcast where Peter Lee of Microsoft Research, and they obviously had early access to GPT-4 and all that. So he mentioned that while evaluating the medical applications, they did this. They would run 2 independent sessions and use the output of one session to be evaluated or assessed by the second session. And they were quite happy that it was able to catch errors and stuff. So
No, that's a good point. Yeah, I think maybe the self evaluation stuff would be really cool, and maybe trying something where we use models from different companies and use those kind of as annotators. At least from what I understand, for in some domains, they usually send the same thing to be labeled to 3 different people, and if 2 out of 3 or 3 out of 3 people agree, then they take that as the truth and throw out everything else. So maybe we could try something like that.
One possibility, Zach, kind of in the direction of your ELO idea, maybe, could be, what if we had 10 models from 10 different companies, and we did all pairwise evaluations, and then we used kind of the model's consensus to create a ranking. If there's one model that all the other models agree is best, maybe better than everything except for themselves, if they all evaluate their own model to be the best, then that would be the model that we would consider the most highly scored. Of course, this could veer off into some direction where there's a subset of models that all start rewarding some particular behavior that we don't really want. But absent some alignment between 10 different organizations, it might be that the models that are evaluated as the best by all other models might actually be the best.
Oh, interesting. So you say that you have a sub, n models, and then each model ranks every other model's response, and then you do that for a bunch of prompts, and then you have this right. That'd be cool. Yeah.
It's harder to hack if you have to please every single other model, especially if you don't know which model is evaluating you right now.
Right.
Thinking back to Corbinian's presentation, your suggestion of flipping the heuristic, maybe the model that everyone hates would actually be the best model because it's so good that the other model don't want to admit.
There's jealous models.
Jealous models, exactly.
Yeah, but yeah, if we have the matrix of all the rankings, pairwise rankings, something interesting we found there. The most hated one, the most preferred one, probably would have some properties that we never were able to find out without this.
Yeah,
I was Jason's comment kind of prompted some security thoughts in my head. Could an attacker incentivize, could it be that some models form a cartel and start voting up or down as a cartel? I don't know.
Definitely could. This has the feel of Byzantine fault tolerance, where if over half of the actors conspire, then they can make the system do whatever they want. But you could have guarantees where the maximum conspiring cohort is 1/3 or less or something, and then I think you can probably make some guarantees. Like,
do you need like a sentinel to detect cartels?
well, you could easily, so plotting all this pairwise evaluations, you could order that matrix in the order of clustering, so using hierarchical agglomerative clustering, for example, and then you would see blocks that all co-evaluated each other positively and maybe others negatively, so it would be very visible whether the block is the correct block or the incorrect block is. I'm not sure how to detect that.
Collusion rings in language models.
Yeah,
Yeah,
the feeling of also like to some extent a feeling of coevolution where you have things evolving to do well against other models or agents that are adversarial. Also, I think a lot of labeling pipelines using mechanical Turkers, for example, will give scores to Turkers based on other Turkers. And the idea there is that if you're not sure who's judging you, you're going to assume that the person judging you is like in the majority. So like they're going to reward good labels and punish you for bad labels. And that guarantees everyone acts according with the norms, the generally accepted norms for maybe making good labels.
Mm.
The system is stable and convergent because the only stable equilibrium is to assume the other models, the other agents are behaving rationally, I think.
Yeah, that's super cool. I didn't even think about like this whole coordination or I haven't thought about the Byzantine stuff in a while.
Yeah.
Yeah, very cool. Thank you guys so much.
Thank you.
Yeah. Great, very inspiring, presentation actually from both of you. Like,
Yeah.
a lot of cool ideas.
And a few hours ago, last night, I was panicking, thought we don't have enough signups, but this is perfect. I'd like to limit our signups in the future just to be 2. I think the discussion is much better than when it's rushed.
Than the 10-minute version where we have to like stop everyone on the exact minute. And
yeah, keep saying it's time, save all the questions till later. Let's not save, let's splurge questions.
me writing 30 seconds on the screen.
All right, any final comments, or questions, thoughts?
Oh, hi, Roseanne. Thank you. And Jason, thank you for providing this platform. I have a quick question on like the Discord channel on the like seeking collaborations and how this research jam this. Like I saw like on your Twitter post that like there were a bunch of like collaboration that happened through the seeking collaboration channel, and does it usually like start there, or like I was wondering how that process is like.
Yeah, I don't track all the data, so I might not be most up to date on where things happen, but definitely that's a place I've heard stories that collaborations have started. Research Jam is also a good place because once you've heard someone's idea, it's very clear to you whether you want to collaborate with them or not, and the reaching out process is also can be done easily, as we have all the slides and presenters' names on the website. Today I have yet to update that, but yeah, what else? All our other events are basically geared to have you guys meet each other and find your next collaborator. So they all help in some, yeah.
You're also welcome to show up to this event and do the 4-minute open mic. Like anyone can talk about any topic they want for 4 minutes. So just pitch your overall interest, if it's a project or a general direction. If you don't have a project yet, but you do have a general direction, I would encourage you to check out the reading groups, the interest groups. For example, if you want to work on NLP, there's an NLP interest group. You can kind of go to some of their events. And there's also Open Clubhouse, which will be, I don't know when the next one is.
8 weeks or 7 weeks.
Every 8 weeks or so. That's just like hang out, talk. Anyone can talk about whatever they want. Oftentimes people bring up research topics there, and we just chat about them. And then
Open Clubhouse happens on Clubhouse or Discord?
The confusing name is on Discord. And so it's open.
Okay.
Because Clubhouse back then was not open. Now it's not even, I don't know if it still exists.
we should rename it because it's no longer relevant. Like,
No.
we outlasted Clubhouse as a platform, I think.
Okay.
Yeah.
Thank you very much.
Yeah, if you guys have good names for Open Clubhouse, send them our way.
Voice room, audio room. I don't know. I had a question also. This is my first ever attending a MLC event, although I've been kind of a lurker on Twitter and stuff. But I was just wondering, I am a little obsessed, unhealthy obsessed maybe, with medical applications of AI, and specifically on cancer, like cancer detection, cancer therapy, drug discovery. So I was just wondering, is anybody on this call interested in medicine broadly, like AI applications of medicine, and are working on it right now? And what's the best place to find, like on the Discord, I found, I think, one channel, but it didn't seem very active.
Yeah, I don't know about how active it is, but people definitely talk about medical things there. If you
Okay.
be prompted, if you ask a question there, maybe you'll make it active.
And I could volunteer to give a talk on some paper which is a medical application of AI.
Yeah, you can become a mod of that channel, of that interest group, and can host small events. We can give support so that you can have like a paid Google account, and where you can have long meetings and record the meetings. So we can give all those supports.
Okay. Google account, like you mean Google Meet, to record the Google Meet?
Yeah.
Okay. Thanks, Rosie.
Okay, let's end here. I have to run to a meeting. It's great seeing you all.
See you all. Have a good morning.
See you next
Thanks,
time.
Roseanne. Thanks, Jason. Thanks, everyone.
Thank you.